Okay, so let's continue our discussion of simple mechanical objects using the principles of forces and accelerations and energies and momenta by thinking about how balls bounce and basically how collisions happen, continuing a discussion that we had in the last chapter. I'm sure you've experienced, just in the context of your daily life, that different objects, for instance, bounce or collide very differently. And if you need a refresher, there's a link in the lecture notes to a physics professor systematically dropping lots of different sports balls from the same height and just recording how, they bounce. And, different things behave differently. A golf ball dropped on a hard surface will, bounce several times, whereas if you drop a hacky sack, it'll just land with kind of a thud. In that whole process of, starting with something that has gravitational potential energy, converting that gravitational potential energy into kinetic energy as the ball falls and picks up speed, what happens in the rebound process or in the collision process? Can we ever have a ball that bounces higher than the height it was dropped from? No, at least not in a simple version of that experiment, because that would violate the conservation of energy, right? If I started with, say, a ball dropped from some height, starting at rest, it would have a total energy, which was just the gravitational potential energy. And if after, it fell down and then bounced back up, it was at a higher position, somehow the energy of the system would have increased. How could that have happened, right? As long as this ball started from rest and there's nothing else in the problem, seeing a ball bounce higher than it started would violate the conservation of energy. But how high can you get a ball to bounce? And what determines how high different things will bounce after you let them kind of collide with the ground? So you might have kind of already started guessing from the way we talked about how general our discussion of springs was, that every, for instance, sports ball that you drop has some equilibrium shape. When no forces are acting on it, it has some particular shape that it wants to adopt. A tennis ball or a soccer ball, those are roughly spheres that are filled with pressurized air. A rugby ball is kind of rugby ball shaped, and so on, right? And during a collision, whether that's a collision with the ground or with a racket or with your foot, that shape gets distorted, right? So some of the kinetic energy, for instance, that exists before the collision gets stored as this kind of elastic energy as you deform the ball away from its equilibrium shape. And then as the rebound happens, some of that elastic energy gets converted back into kinetic energy. So I pulled up a video from YouTube of a tennis racket serve moving at 142 miles an hour after this ball gets hit, recorded in slow motion. And it's amazing, so let's watch what happens. So the racket is going to come in and kind of strike the ball in this direction. This ball was just tossed straight up. And what happens? It's just amazing. And I feel like I want to be, playing a fun sound effect as this happens. So let's just rewind this a few times and maybe even watch it on YouTube played back a little bit slower. So look at that. You can see that the tennis ball, from its spherical shape initially, gets compressed to almost a disc that's as flat as the tennis racket itself in this case, storing a large amount of elastic energy in the deformation of that tennis ball. If you feel a tennis ball in your hand, you know that it takes a good amount of work to bend it and deform it, right? Afterwards, the ball flies off the racket. You can see it's still not a sphere. And in the next few frames, you can even see the tennis ball kind of oscillate in its shape as it flies away. That's just super cool. And then there's a slow motion version of this that you can scroll through on your own. So again, before the collision, the racket has a lot of kinetic energy. As the racket continues to move forward, a lot of kinetic energy goes into the deformation of the tennis ball, and then some of that elastic energy gets released back into the kinetic energy of the tennis ball as it flies away from the racket. How cool. So, often what we do is basically characterize what is the amount of energy before a collision and after a collision that's carried in the kinetic energy part of this problem. So we'll often define, we'll define collision energy as the kinetic energy that will be absorbed during a collision. Okay, so absorbed during a collision. And we'll define the rebound energy, and so we'll define rebound energy as the kinetic energy that's released as the ball, returns back to its equilibrium shape. As the kinetic energy released as the object returns to its equilibrium shape, or after the collision returns to its equilibrium shape. Okay, and since energy is conserved, at first you might think, well, these two energies should be equal to each other, right? But that's not the case, right? We know that the total energy of a system is conserved, but these are just two forms of kinetic energy, the kinetic energy that gets absorbed before a collision and the kinetic energy that gets released in the process and after the collision, right? So the total energy is conserved, but there's no reason that, rebound energy has to equal collision energy. So I'll write rebound energy does not equal collision energy. Okay, so where does some of the extra energy go? You won't be surprised to learn, since we've been talking so much about friction the whole time, that a lot of energy gets lost into heat, into thermal energy. You also know that, when a tennis racket hits a tennis ball, there's a loud, sound, right? There's like that thwack. And sound waves carry some of that collision energy away too, right? It takes energy to produce a sound wave, and so some of the energy of the collision actually goes into that channel as well. So the amount of collision energy that actually gets returned as rebound energy turns out to be a nice way of quantifying just how well or poorly any particular ball bounces, right? So a perfect elastic ball, or an ideal elastic ball, would have, like, the ratio of these two things being 1, would have, rebound energy divided by collision energy equal to 1. And in the real world, this never happens. Again, you always lose at least a little bit of energy, either due to heat or the vibrations of an object, right? Like you saw how the tennis ball was like oscillating for a little bit before it stopped oscillating after the collision. You lose energy to heat, oscillations, sound, so on and so forth. So if you have a collision that has this character, it would be called a perfectly elastic collision, right? And you can imagine some scenarios where you have, the amount of energy you lose is very small, and so you have almost perfectly elastic collisions, but this is just an ideal, right? The other extreme, at the opposite of this, is a perfectly inelastic collision. So when two objects stick together, and move with the same velocity after a collision, after a collision. This is called a perfectly inelastic collision. And this kind of thing, in fact, does happen more frequently. So for instance, suppose I have like a block that has some mass, and maybe it's traveling at some small velocity this way. I'll call it v1 and maybe m1. And suppose I like throw like a lump of clay really fast towards that block, m2 traveling at v2. After the collision, what I'll have is like m1 with a lump of splatted clay sticking on top of it, m1 and m2, both moving together at some new velocity. I'll just call that the final velocity, right? So this would be an example of a perfectly inelastic collision. You've lost, in some ways, the most possible amount of kinetic energy that's still consistent with the fact that the total momentum has to be conserved, right? So the constraint here is that, momentum is still conserved, which means, let's write this out a little explicitly, since this showed up in the homework. The total momentum initial has to be the total momentum final. What is the momentum initially? It's m2 vector v2 plus m1 vector v1. And the conservation of momentum tells me that this has to equal m1 plus m2, the total mass of this object, all moving at whatever this final velocity is. So perfect inelastic collisions are governed by this type of relationship between the initial masses and velocities and the final velocity after a collision where you've lost the most amount of kinetic energy you can, but still obey conservation of momentum. Right? And again, where did that extra kinetic energy go? It went into heat, it went into sound, so on and so forth. Okay? You know, in the real world, most things typically experience some sort of inelastic collision in between these extremes. You don't have a perfectly elastic collision, but you also don't have a perfectly inelastic collision, right? Some amount of the energy in the collision, the kinetic energy in the collision gets, wasted. The ball bounces back, for instance, if you drop it to a slightly different height, and it's something in between these extremes. So, for example, let's think about a tennis ball. It turns out, this is an experiment you can do at home if you start with a tennis ball that's like a fresh one, and you drop it from some height, and you measure after the first bounce, how high does it get? It gets to just a little bit more than half its original height. And after it bounces again, it kind of gets to a height that's half of that. So if I take a tennis ball and bounce it, it'll kind of go kind of like this. So this height is a little bit more than this, half of this. This height is a little bit more than half of this, so on and so forth. So for example, tennis ball, just to give you a sense of some of the typical ratios of these things you might expect, a tennis ball has a ratio of about 55%. It maintains 55% of its kinetic energy after a collision as it had beforehand. Other objects are a little bit better or worse. A solid rubber ball keeps maybe closer to 80% of its energy. A baseball, maybe it's closer to 30% of its collision energy, so on and so forth. Right? So you can use this ratio, what is the amount of energy you have as kinetic energy after the collision compared to how much you had before the collision. You can use that ratio to characterize, well, what's the typical behavior of a bouncing object, of that bouncing object, right? Historically and kind of traditionally, this has been characterized not as the ratio of energies, but actually the ratio of speeds. So traditionally, we define what's called the coefficient of restitution. Coefficient of restitution, which is a funny way of writing this number that characterizes how an object collides and rebounds, as the coefficient of restitution of some object is given not by the ratio of the energies, but by the ratio of the speeds. So it's the rebound speed of object compared to its collision speed. So divided by collision speed of object. And this definition has been around for a lot longer because we've kind of understood scientifically speeds and velocities for a much longer time than we've really deeply understood energies. So people typically define things as rebound, the ratio of speeds rather than the ratio of energies. Of course, that there's a simple relationship between, what are the speeds of an object compared to the kinetic energies, right? The kinetic energy of an object, kinetic energy is 1/2 times the mass times the velocity squared. And for the velocity squared, you just need the magnitude of the velocity. So the kinetic energy is proportional to the speed squared. So you can kind of figure out, okay, given this ratio of speeds, what would the ratio of kinetic energies be before and after such a collision, right? And you can see that if, I look at the ratio, kinetic energy before divided by kinetic energy after, translational kinetic energy after, this is going to be equal to, 1/2 v beforehand, v initial squared, divided by, and this is supposed to be upside down. My apologies. Right, because the way this ratio is defined is the rebound over the collision, so that's actually the kinetic energy after, divided by the kinetic energy before. Right, so that's equal to 1/2 times the mass times the final velocity squared, divided by 1/2 times the mass times the initial velocity squared, or the initial speed squared. So you can see that there's a simple relationship between the ratio of kinetic energies, which we kind of wrote up here as a characterization, and this traditional coefficient of restitution, which measures ratios of speeds rather than ratios of kinetic energies. And it's nice, right? These masses cancel out, these 1/2s cancel out, so it's pretty simple relationship between these. Okay, you might wonder, in this class, we're not going to try to calculate, like, given an object, how do we calculate what the coefficient of restitution of something is? But we can think about what kinds of properties go into determining this coefficient, right? So of course, what an object is made out of matters a lot. Some substances are just better at storing and releasing elastic energy than others, right? So if you have a rubber ball versus a clay ball, the rubber ball will bounce better. It'll have a higher coefficient of restitution, right? It's also the case, it turns out, that energy storage is much more efficient when you're just kind of compressing an object rather than when you're bending the surface of an object, okay? Because it turns out that actually when you bend a surface, you're generating more kind of internal friction and you lose more energy to heat than if you're just kind of compressing a solid object. So what does that tell us? That tells us that, for instance, a ball made out of solid rubber will bounce better than a kind of rubber shell, a ball that's just like a shell of rubber with nothing inside, right? That's great. That's actually why, most sports balls that are shells are filled with pressurized air, right? So you have a basketball, you have to inflate it to a certain pressure. You have a tennis ball, it's got pressurized air inside. You have a soccer ball, you have to pressurize it. And maybe you've experienced the fact that, like, when a sports ball gets deflated a little bit, it's kind of less lively. It bounces around less well. What's going on there? It turns out, pressurized air is also a pretty effective way of storing elastic energy. So, if you pump a ball full of air, the surface bends and you lose energy to friction that way, but you're also compressing the air that's inside that, say, rubber shell of a tennis ball. And that compressed air does a reasonably good job of storing and releasing energy. But you need it to be really compressed air, otherwise the ball won't bounce very well. Okay. The last thing that I want to kind of call back to something we've already learned has to do with, like, collisions as they relate to frames of reference, right? So, for instance, let's suppose that, I've got a person standing over here, and there's a soccer ball that's, coming towards them, and this person wants to kick the soccer ball, back in this direction. So what do, right? They, like, wind their leg up, and they move their foot forward, right? So at the kind of instant of collision, instant before collision, at the instant before collision, let's kind of zoom in on what's happening, right? We've got a soccer ball, which is traveling in this direction with some velocity, right? So I'll just call that V, soccer. And we've got this person's, like, leg, which is swinging forward to meet the soccer ball, right? V leg. So, we have these kinetic energy formulas that are like 1/2 mass velocity squared. Well, when it comes to collisions, what is the velocity that matters here? Actually, what we can do is think about, like, transforming into a frame of reference where it's easier to understand what's going on. So let's go to the frame of reference. Frame of reference where the soccer ball is stationary. Soccer ball is stationary. That is, we imagine being in a frame of reference, an inertial frame of reference, so we're just going to move at a constant velocity, kind of following the velocity of the soccer ball. So in this frame of reference, the soccer ball has 0 velocity, but there's this leg which is flying towards the soccer ball with a velocity which is equal to the sum of these opposing velocities, which is equal to the sum of Vs, at least the magnitudes are equal to this. So it's kind of Vs, let's say, just to get the signs right, VL minus Vs, right? The important thing is that the magnitude of the velocity of the leg in the reference frame of the soccer ball is like the sum of the magnitudes of these at least opposing motions. Intuitively, you should kind of imagine this like when you're driving on the highway, right? And maybe it's a 2-lane, 2-way highway, so you're in a car going this way, and in the other lane there's a car coming towards you. You are approaching each other at a rate which is the sum of your speeds, right? And so a collision would be really very dramatic and violent, right? On the other hand, if you're like approaching a car like you're driving in the same direction, you're on the highway and they're just going a little bit slow, the rate at which you approach them is like their velocity minus your velocity, right? Or your velocity minus their velocity, depending on how you want to think about it. So this relative difference in velocities can either like reduce the effective velocity of the collision in the case where you're moving together, or it can increase it in the case where the two things are moving to meet each other, right? So in this case, in the frame of reference of the soccer ball, actually the velocity of the collision that matters is this combined velocity, velocity of the leg minus the velocity of the soccer ball, as expressed, where these terms are what I've drawn up here, right? So if the soccer ball is moving at 50 kilometers per hour to the left, and the leg is moving at 20 kilometers per hour to the right, in this frame of reference, the velocity of the leg, the velocity at which it is approaching the soccer ball, is going to be 70 kilometers per hour to the right, as we kind of see in this example, right? So great. So then how do collisions work? For instance, what is the velocity of the soccer ball after the collision? Well, still in this frame of reference, right? After collision, there's a certain amount of this velocity that gets lost, right, from that coefficient of restitution. We would say the ball, moves away from the leg at CR times this V. So I don't know offhand what the coefficient of restitution of a soccer ball is. For convenience, let's just say it's, 50%. So maybe it's 0.5. It's probably a little bit different than that. 0.5 times 70 kilometers per hour to the right. So in this frame of reference, after the collision, I have this leg still moving with some velocity, and I have this soccer ball moving away from the leg with a velocity given by, V soccer ball after, given by, say, 35 kilometers per hour to the right. Okay. Now, there's actually one more step that we have to do in this example of like frames of reference of collisions where both things are moving, and that's, let's go back to frame of reference of an observer, like a spectator in the stands, of the observer, of an observer. I guess there's not just one. Of an observer. Someone who's not moving. We're not moving with the same velocity as the soccer ball, right? So remember, in this frame of reference, that's where we have this picture. The leg is approaching the ball is approaching the leg, and both things are moving with some, say, fixed velocity. So in this frame of reference, the soccer ball moves away from the leg, at, what we worked out up here, Vs after 35 kilometers per hour, okay? But the leg is still moving, right? When someone's playing soccer and they strike a ball, they follow through, so their leg, continues to move with a forward velocity even after the collision, right? So the leg is still moving, but the leg is still moving, right? And that means, okay, the ball moves away from the leg at a certain velocity, and that means the actual exit velocity, like the actual velocity from the perspective of an observer that this ball suddenly has, motion flying away with, is given by the sum, is given by this 35 kilometers per hour plus whatever the velocity of the leg after the collision is. Sorry, the computer's got a little bit of lag at the moment. Velocity of the leg afterwards, right? So, if I have a little demo here, let's pretend this is the soccer ball, this is the leg. So if, they're moving together like this, in the frame of reference of the soccer ball just sees, the leg move faster, the sum of these two speeds, since they're moving in perfectly opposite directions. So in this frame of reference, the soccer ball just sees the leg approach it really quickly. We do this coefficient of restitution calculation to figure out that, what happens in the original frame of reference of the moving soccer ball is the leg approaches it with a fast velocity, and then they both start moving in this direction. And this velocity with which the soccer ball moves away from the leg is this 35 kilometers per hour. But the leg is still moving in this direction. So the actual velocity that the soccer ball is moving with, as seen by an observer in a stationary inertial reference frame, is given by the sum of this calculation plus however fast the leg is still moving after this collision. Okay. So that's great. So that kind of is a introduction to more complicated collisions than we saw in the last chapter. Some of the key ideas, again, are that bouncing balls and colliding objects in some ways are kind of like springs. During a collision, they can store some elastic energy and then rebound, releasing some of that elastic energy and turning it back into kinetic energy. Right? The details of how much rebound energy you're able to maintain depend on a lot of properties of what's actually colliding in this situation. And we talked about these two extremes, these perfectly elastic collisions, which kind of don't exist in the real world because you always lose a little bit of energy to something, sound, heat, vibrations, and these perfectly inelastic collisions where you say you lose as much kinetic energy as possible while still being consistent with conservation of momentum. And then we kind of talked through a few examples of thinking through how all of the concepts we've learned so far, combining both conservations of energy and momentum as encoded in this measurement of coefficient of restitution telling me something about how balls bounce, together with what we know about frames of reference to figure out, how fast do objects move after they collide, not just when you have one object colliding against a stationary surface, but when two objects are actually moving with some relative velocity to each other.